Hi everybody and welcome to a new video in the Deep Learning for Audio with Python series. This time we're going to implement backpropagation and gradient descent. And to do that we're going to expand on the work we've done a couple of videos ago when we implemented a multi-layer perception class, this MLP object here. And in that case we built a constructor where basically we built like the structure of the network, and then we mainly focused on this forward propagate method, which is basically forward propagation, which computes the inputs which travel from left to right and gives us a prediction. Good. So what are we going to do specifically like this time around? Well, it's a bunch of like different things, and so it's better just like to write them down so that we'll have more or less like a direction that we know we are following. Because by the way, this is going to be like a quite intense video and probably quite long as well. Good. So the first thing that we want to do is to save the activations and the derivatives. And derivatives, right? So this is like while to compute backpropagation, we need information about activations and obviously about like the derivatives as well when we'll compute a gradient descent. Then what we want to do is to implement backpropagation. So once we have backpropagation implemented, we want to implement a gradient descent. And once we have that, it's time to go higher, like from a higher level, and implement a train method, which will use both backpropagation and gradient descent. And then we want to train our network with some dummy dataset. And finally, make some predictions. Good. So this is the plan for today's video. So let's get started from the first one. So save activations and derivatives, right? So first of all, we need a representation for data representation for these activations and derivatives, and we need to create this representation here in the MLP constructor, right? And so as we did for the weights here, where we basically created some random weights, we should do like a similar thing for the activations and derivatives. So let's get started. Activations, and we'll start with an empty list. I don't like that is like that. Nice. And now we'll do a for loop, and we'll go through all the layers here. Right? We'll go through all the layers, and then we want to create a dummy activation array for each of the layers. So how do we do that? So it's quite simple. So it's we'll create an array A, which is given by np dots, and we'll do zeros here. So it's an array of zeros, and we'll specify that we want an amount of zeros here that's equal to the number of neurons that we have in each layer, right? For each layer. So then we'll do a activations.append, and we'll append this one-dimensional array here to activations. So in the end, activations is going to be a list of arrays where each array in the list represents the activations for a given layer, right? So now we want to store all of this information in a instance variable called activations. And so self.activations is going to be equal to activations. Nice. So now we should do something similar with derivatives as well. So I'll just copy all of this and paste it here. So instead of activations, we'll have like derivatives here. So we have this like empty list derivatives, and now we want to loop through the layers, but all the layers like -1. Because if you guys remember, when we have, for example, a network with 3 layers, we only have 2 weight matrices, because the weight matrices are in between layers, right? And so in this case, we are going to have a number of like derivatives or that are like equal to the weight matrices, right? Because the derivatives are the derivatives of the error function with respect to the weights. Cool. So let's change this. So we'll call this D. And now we're not expecting a mono-dimensional array, rather like a 2-dimensional array, which is basically a matrix. And this matrix is going to have the dimensions. Like, so for the rows, we expect the number of neurons that we have in the current layer I, and for the columns, we expect the number of neurons that we have in the subsequent layer, right? So that's that. And now we want to just change this, and we want to append derivatives. And here, these activations again should be changed into derivatives. Nice. Okay, so now we have a nice way of storing derivatives as well. Good. So now that we have all like the representation in place, we should go and tweak our forward propagate so that we can save the activations while we create, like while we compute these activations for each layer. So what about the activation self-dot activations for the first layer, for the input layer? Well, we know that this is basically just like the inputs, right? So we can't save the activations for the first layer as the inputs that we are receiving here as an argument for forward propagate. Nice. So now there's the next step, which is this forward propagate iterates through like all the network layers and calculates the activations. And now here, at this point, we want to save the activations. And now we're going to save the activations at I plus 1. And this is going to be the activations. So now you may be wondering, but if we are currently in I, right? At why are we storing this like at I plus 1? Well, let me show you why that's the case. So if you may remember that the activation, say for example, like the activation of the third layer is equal to the sigmoid function, given like we are only using sigmoid functions as activations functions. It's the sigmoid function of H3. But now H3, if you guys remember, is equal to the matrix multiplication between A2 and we have W2, right? And so here, basically, we're saying that we are at, say, for example, this I is equal to 2. And so here we're considering like the second weight matrix. And then the activations connected with the second weight matrix is indeed the activation for the third layer. And so here we need to like add 1 to the current I. So in our example, 2 plus 1, 3, right? And so this is why we're doing this. Good. So nice. So now we have done basically the first part of the first task, which is like saving activations and derivatives. Now saving just activations, because derivatives, we haven't saved them. We've just like created the representation for saving them. But we'll do that when we implement backpropagation, which is happening right now. Cool. So now we need to implement a new method called backpropagate. Right. So now, first of all, we want to pass an error here. So, and we'll see like what this error is like in a few seconds. But first of all, how does this work? So we said like in the previous video that with backpropagation, the idea is to have the error and backpropagate the error from the output layer, towards the input layer towards the left, right? So basically so the way we can translate this in code is that we can basically loop through all the layers starting from like the last one towards like the previous ones, right? And so how do we do that? Well, it's quite simple. So we will do a for loop in range of the length of self dot derivatives here. So, but this is just like going from left to right, because we are incrementing I from 0 like towards like the number of like elements we have like in self.derivatives. But we want to go the other way around from right to left. So how do we do that? Well, we just do a reversed of this guy here. Cool. And now, so let me just check. So we may have an issue with the number of parentheses here. No, it's fine. Good. Okay, so now we are just like going through, we are looping through like the neural network, but starting from right and then moving all the way back towards the inputs. Now, what should we do? But in order to understand what we should do, we should remember like how backpropagation works. And so now I'm going to pass in some things that I don't want to write from scratch because it will take too much time. But if you guys remember, let's assume we are like at the rightmost weight matrix, right? So say, for example, we have like this network with 3 layers, then we are like at W2. And then we want to calculate the error with respect, the derivative of the error function with respect to W2, or like in this case, like if we want to keep it general, we could say WY. And this is given by this formula down here, right? So if you guys remember, it's basically like this is the error, which is the difference between y, which is the actual outcome that we are expecting, and the prediction. And we multiply that by the derivative of the sigmoid function calculated in the net input I plus 1. And then we do like a matrix multiplication of all of this with the activations calculated in I. Nice. Good. So the error that we are passing here, this argument, is basically this guy here, this error here. So now the next thing that we want to calculate is this sigma prime here, right? But what's this sigma prime calculated in this net input here? But well, we can rewrite this, like if you remember from the previous video, we can rewrite the sigma prime here as this derivative. This first derivative is the sigma itself calculated in a point and multiplied by 1 minus like sigma calculated in that same point. Good. But if you remember, guys, the sigma calculated in this point here in I plus 1, it's basically the activation calculated in I plus 1. And so basically we can get this and just like pop it into like this function over here, and we'll get the sigma prime information about sigma prime. So all of this basically to say that we need to retrieve the activations here, but these activations, we can access them because we've saved them in self.activations, but not not the activations in I, but in I plus 1, so in the subsequent layer, right? And so we have this as activations. Nice. So now if we want to calculate this guy here, so the sigma over here, so what we need to do is basically do like a sigma at the first derivative of the sigmoid function calculated in these activations, right? But to do that, we'll do like something slightly we'll do like something like slightly different now, which is basically calculating delta, and we'll define delta as these two elements together. So the error multiplied by the first derivative of the sigmoid function. So let's do that. So delta is going to be equal to the error, and that's multiplied by self dot let's call it sigmoid derivative, and we'll pass in the activations. Good, this is nice. But there's an issue here, which is that obviously we don't have this function yet because we haven't like defined it. So let's build like this method now. So we'll define a new method called underscore sigmoid derivative, and we'll pass in x, and we'll return just like look here what this should look like. And so we'll return x multiplied by 1 minus x, right? And so we have our sigmoid derivative function here. Nice. So we have delta. Nice. So which basically means like we have all of this. Now the next step that we need to do is that of like calculating the this guy here, right? So we'll need to, so in order to do this, we'll need to get this other activation, which is the activation taken like at layer like I. So we could call this current activations, and that's equal to self.activations, but at I, right? Nice. So now, at least in theory, we have like all the elements to calculate the derivative in I, right? And the derivative in I is going to be given by the dot product of current activations with delta. Nice. And so now we have like the derivative, but really we don't have it yet because I'm going to explain why, but we'll need to do like some trickery with like NumPy to organize like these two arrays in a way where we can actually perform this matrix multiplication between the current activations and delta. So what we want to do as the first thing is basically rearranging this array and rearranging it in such a way that it will become a two-dimensional array where we only have like a one column, right? So it's going to be basically like a vertical matrix. So what this basically means is that we want to, okay, yeah, let me just like comment this. So we want to move from an array, so we now have this current activations that's an array like this, say could be like 0.1 and 0.2, and we want to rearrange it so that it has this structure. So you'll see it here. Sorry, like this. Okay. So basically this is going to be like a 2D array, and it's going to be like basically like a vertical vector, right? Good. So how do we do that? Well, we need to do like some trickery with NumPy. So we'll do that. The current activations, let's call it reshaped. It's equal to current activations, and then we need to call the reshape method, which is a native method in NumPy, and so here we need to do this thing. So current activations dot shape, and we take like the shape like of the first like index, and then we do like a -1. So doing this, we'll just move, like we'll restructure our array from like this to this, right? And so, and now we just need to change this over here, and we've like input the current activations reshaped. Now we need to do something similar for delta as well. So we need a delta reshaped. Good, but let's take a look at what we want to do first. So for delta, so let me like rewrite this like this. So we are starting with a similar array, so which is like a one-dimensional array. And then what we want to achieve now is a two-dimensional array where we, well, give me a sec over here, where we have this, right? So it's basically just like a two-dimensional array with a single row. So how do we do that? Well, we can do like something very similar to this, to what we've done with the current activations, but obviously instead of current activations, we should use delta. We use delta, and then here we have a, obviously, like after we perform this reshape until now, here we have a vertical matrix. And so if we do dot T, capital T, this will transpose the array. And so we'll basically move from a structure like this one to a structure like this. Nice. So now we have everything in place to do to calculate like our derivative here. And so yeah, this is like basically all we need to do for like the first part over here, like of our back propagation. So for the utmost like weight matrix, so when we do like the derivative of the error function with respect to w calculated in I, right? Okay, so now we know though that we want to just like go back one step and do another like derivative of the error function, but this time in w of I minus 1. So, and how do we do that like with a formula? And we've already seen this, and I'm gonna just like copy paste it here, just like because like it's easier, right? And so as you see here, so when we are calculating the next derivative towards the left, what we are gonna bring back from the previous derivative that we've calculated is this guy here, right? So the delta itself. So delta is going to be like moved to pushed back towards like the previous layer. But along with that, given like we are like at I right now, we could also calculate all of this. So basically doing we're going to calculate a new error here, which is going to be given by the NP dots. So we want to do a matrix multiplication here between delta itself, and we want to do that with the weights, with the weight matrix. So it's this guy here for the I layer, and here we need like to do just like the transpose matrix for that. Cool. So now this error here is basically all of this guy here. So now that we are here, you'll see that we are just like going to start another loop, and we are going down with I. So if the first time it was like I equal 2, now we're going for I equal 1. So we're going to do the derivatives for W1. Right. And so now we're just going to do like the same thing once again, but this time we have our error, and our error is given by all of this guy here, which we calculated in the previous passage, in the previous iteration. And now we are calculating delta, which this time around is going to be like this guy, and then we are going to calculate this derivative here by doing the matrix multiplication between the current activations, and which is this, and the delta reshaped like over here. Nice. And so now we can go all the way back until we are like at the input level. So I know like this was like a little bit, I would say, like more difficult to understand than like a simple case where we have like hardwired or like layers. But with this backpropagation, we can have potentially infinite layers, and this backpropagate method is going to work for all of them. Nice. So now, as the final thing, we could potentially return the error, which in this case is going to be the error backpropagated all the way back to the input layer. Good. Okay, so this was like backpropagation. So I suggest now like we do try to like run the code up until like what we've done like now, to see like if everything like is okay, because we may have like some bugs because we don't know. Right, so okay, so first of all, yeah, let me do this if name is equal to main, and so here we are like ensuring that we run this like as the main script. Good. So what do we want to do here? Well, first of all, we want to create an MLP, so multi-layer perception, and then we want to let's just like create dummy data, dummy inputs and targets, and then we're gonna pass this data so to forward propagate. So we will do like a forward propagation, and then we'll do a back propagation. Good. Okay, so let's start by creating an MLP. So that's quite simple now, because we already know that we have this guy here. And so let's say here we should pass the number of like inputs, the number of hidden layers, and the number of outputs. So let's do something like this. So 2 neurons for the input layers. So now we want only a 1 hidden layer with say like 5 neurons, and then we have just 1 neuron for the output layer. Good. Okay, so now let's create some dummy data. So we'll create an input, and this input is going to be an array where we pass in a couple of numbers, right? And why should we pass a couple of numbers here? Because we have like 2 neurons, and basically each of these guys in the array is going to go to one of the 2 different neurons, right? Okay, so we have the input, and now we want the target. And the target is going to be itself an array, and let's say 0.3. So you probably are seeing what I'm doing here. So I'm expecting the sum like of these two numbers, right? So I hope like my network is gonna like learn how to do the sum operation. And yeah, that's what we are gonna use like as a task, dummy, like toy task, like for this video. Good. So, but here we have just a single input and a single target. That's all we need for now. So what should we do now? Well, first of all, we should do an mlp.forward propagate, and we want to pass the input in. And so we'll pass this guy here, and then we'll do a back propagation here. So mlp.back-propagate, and obviously we are expecting an output over here, which is basically like the after like all the computation has been done, like on the inputs, we're getting like the prediction, which is this output. Well, I forgot to mention one step here before doing backpropagation, and you should know by now what that step should be, and it's calculate the error, right? So, and how do we calculate the error? So, well, we calculate the error doing a target minus the output. And then when we do backpropagation, we'll just pass in the error, right? Okay, so let's try to see if we get what we expect from backpropagation. So I'd say what we could do here is we could have, for the time being, a verbose argument, which we'll set as false initially, and then we say if verbose, so if we are in verbose mode, then we want to print, what do we want to print here? Well, we want to print the derivatives that we've calculated for like a specific weight matrix. So how do we do that? Well, we do that by saying derivatives for W, and then here we'll say I, and yeah, and I think like we are like this is well, this is equal to this self derivatives calculated in I. Good. Okay, cool. So fingers crossed this should work until like we've made some mistakes in the process. So let's see if this works. Well, obviously I've run this, but I should pass in the verbose equals true, like if I want to see like something coming up. So let's say this. Oh, nice. So what do we have here? So we have the derivatives for W1, and indeed we are expecting this structure like for like this matrix, which is like basically 5 by 1. So it's just like a column matrix. And why is that the case? Well, because we have 5 neurons like in this hidden layer, and just like 1 neuron here like as the output layer. And so we expect like a 5 by 1 matrix there for W1, right? So now for W0 over here, which is going to be like between like the input layer and the first hidden layer, or the only hidden layer. So we are expecting a matrix which should be, and we have it here, 2 by 5, and indeed we have it. So as you see it here, we have like 5 different values for each row, And that's like what we were expecting. So we are like on the right path here, but it ain't finished yet. So we should keep like moving on. And so what we've done so far is we've activated, so we saved the activations and the derivatives. We've implemented backpropagation. Now we need to implement gradient descent, but I promise this is going to be like way faster than backpropagation because it's quite straightforward. So good. Okay, so let's move on with a new method, which we'll call gradient descent. And here, so we need to pass an argument. This is called the learning rate, and we've seen this in the last video. And this is like the size of the step we want to take against the gradient, just like to optimize our error function, right? Good. So now, what should we do? Well, so now we should go loop through all the weights. And so we're going to do that by doing a for loop in, we could say, in a range length of self dot weights. So we are going through like all the different, sorry, the different weight matrices. And then we can say that the weight matrix for the current layer over here, it's gonna be self weights calculated like in I, and we can do like the same thing with derivatives. So we'll just change this too. And so basically we are getting we are retrieving the weights and the relative derivatives for a given layer, right? And so what we want to do here is to update the weights. And to update the weights, if you guys remember, if you're good students, you should know this by now because we've covered this in the last video. But what we should do here is take in the weights, and we should add to the weights the derivatives multiplied by the learning rate. Nice. So let's rewrite this in a more compact way, and so we can just like do this. It's the same thing. So we are oops, sorry. Yeah. So we are adding the scalar multiplication of like learning rate and derivatives to weights. And so these are weights and derivatives are two matrices like with the same dimensions, right? And so we are just like adding them up once we've tweaked the derivatives by applying the learning rate. Good. And so here we have done so we now have like also gradient descent, which is great. So now let's go back to like our script here. So we've done backpropagation. So the next thing we want to do is we want to apply gradient descent. Good. So how do we do that? Well, now that we have our gradient descent method, this is going to be super simple to do. So we pass in a learning rate, and let's say we want to pass in 0.1, for example, as our learning rate. Good. Okay, but let's see if gradient descent like is working properly. And so for doing that, I would come here, and I would like to print. Yeah, let's do it here. So let's do a print. We'll print the weights. So we'll do a W and we'll do format, and we'll pass in I, and then here we want actually to pass the oops, sorry. So we damn. So I, and here we have the weights, and so we want to pass this in, and this is yeah, let's call them original W. So these are like the original weights, and then we can take this, and after, so let's put some new lines here, because like this is becoming like a mess, right? So here we retrieve the weights, we print them, then we retrieve the derivatives, we apply like a gradient descent to the weights, and now we have the updated, oops, here we go, updated weights, and yeah, and so we have like these weights which now should be different. So let's say like if this is working, okay, so now I'd say we don't want to print this, because otherwise we're gonna have like a mess. So let's try this and see. Okay, so we have, yeah, right, there's a difference, but it's, so take like for example this, right, that's like the first, so element 0 0 of like W0 and element 0 0 of like W0 here, like after we've applied it, and as you can see, like they are slightly different, but the difference like is quite minimal, because like we have like a small learning rate. So if we change this learning rate and we put it like as 1, so this should be like quite bigger. Yeah, so yeah, you can see it from here, like W1 here, like the first element here like it's 0.8, and here in the updated W1 like the first element is 0.76. So basically gradient descent is working properly, and this is great news. Nice. But now we actually really don't need this like at all. Yeah, because I mean like it was just like for showing whether like this was working. So let's remove that. Nice. So now what remains to do here? So we've implemented gradient descent. Now we should implement the train method. Nice. So back-propagate, gradient descent, and now let's do train. So the train method is gonna have, oops, there's a mistake here. Yeah, here we go. The train method is gonna have a bunch of different arguments. So first of all, we want some inputs. Then we want targets. And these inputs and targets are our training set, which like our x's like and y's basically. And then we want epochs, and I'll explain what an epoch is in a second. And then we want the learning rate, right? Good. Okay, so what should we do for training? Well, if you guys remember, so we pass all the inputs like one by one to the network, we feed it, and then the network does some forward propagation and then back propagation. But then once we've passed all of the elements, all of the samples like in the inputs, in the training set, we've finished an epoch. So the number of epochs tells us basically how many times we want to feed the whole data set to the neural network, with the idea that the more times we do this, and hopefully like the more like the network is going to be able to make better predictions. So basically what we need to do is like go through all the epochs, and so loop through the number of epochs. And so let's say for I in a range epochs, and so here we should do really like a bunch of different things. So first of all, we should take so we should go through like all the inputs and the targets, like one by one. So how are we going to do this? Well, there's like a nice trick we can use here, and we could say, yeah, let me just like write this and I'll explain what this is in a second. So for j, input target in, and now we do an enumerate, and then we do a zip over here, and we pass in the inputs and we pass in the targets. Cool. So this is like a very compact way of like getting like inputs, targets one by one, and it's like this input and target, and also getting like the index that we are unpacking. So zip unpacks like this two different lists, inputs and targets, and give us like elements one by one for input and for targets. And then if we apply enumerate on top of that, we both get the values themselves and the index that we are unpacking. Good. So yeah, this is like a nice trick. Cool. So now what should we do? Well, we've partially done a bunch of these things already. So let's take these guys here, right? So, and we'll move them here. So what do we want to do? Well, first thing, we want to apply some forward propagation. But this is not going to be MLP, but this is going to be self. So we do forward propagate on the input, then we calculate the error, and this is going to be the target minus the output. And then we apply some back propagation, but this again is going to be like a self back propagate, and we pass in the error. And then we apply gradient descent. Here we go. Change MLP for itself, and the learning rate, yeah, we already have it here. Oh, by the way, I noticed there's a mistake over here. So it's not for I in range epochs, but is in the length. Oh no, sorry. I was right. I thought like for a second that epochs was a list. No, it's just an integer, so it's fine. Good. Okay. Cool. So we have gradient descent, and we've applied gradient descent. So now one last thing that we want to do is to report the error for each epoch so that we can see whether we are improving. So how do we do that? Well, first of all, we want to initialize a sum error variable over here, and we'll initialize that, obviously that's a 0, and then at the end of each like a training session, like for each input, we are gonna calculate this sum error, and we'll add to sum error. What are we gonna add? So we're gonna add self dot MSE, and we'll pass the target and the output. Good. So what's this MSE here? So this is the min squared error, right? And so we don't have this function, this method already, and so we need to build it. So let's implement it down here. So we'll do def MSE self, and we'll pass in target and the output. And so it's not MSR, it's MSE, so min squared error. So, and what is this? So how do we calculate this? Well, this is basically the average of the squared error, right? And so we can use a native method from NumPy. It's called average, super handy. And we'll basically rewrite this like this. So we'll do the average of the target minus the output, and we want to square this, so we'll do this, right? And so this is our min squared error. Nice. So now we have an error that's accumulating like at every step that we take like in our training. And and we want to report it like at the end of an epoch. Right, and so how do we do that, right? So we'll do that by yes, so we'll just like do a print over here, and we'll write error, and we'll say error is equal to something at epoch, and we'll have the epoch over here. Cool, and so we'll do format, and we'll pass in for the error some error divided by the length of the inputs, right? Because this way we are basically like normalizing that. And what we also want to do is we want to pass the number of epochs. So in this case is I, right? So let me just double check if it's all good over here. So we have this format. Yeah, this is not working. Okay, so yeah, so we have the first argument, that's this one here, and then we have I, and this, yeah, closes the format, which, yeah, so this should be fine now. Good. Okay, so now I think we have all the elements, if I'm not mistaken, we have all the elements in place for doing a run of our neural network. Good. So, but before doing that, I just want to double check a thing, because like I did this fancy thing here, but I'm not using like J like anywhere. So I don't really think like we're gonna need like this J. Yeah, I don't see a point here. So yeah. Well, at least like you've learned a trick, but it's not really needed. So we'll just like simplify this, and we'll just drop this enumerate, and like that. Right. So now this should work properly. Good. Okay. So now let's go back to our tasks. So we basically did all of these things here. So now we want to train our nets with some dummy data set and then make some predictions. Okay, so let's go back here. So now we are back like in the scripts. Okay, so we've already created an MLP, and now we want to train our MLP. And how do we do that? Well, we do mlp.train. We need to pass in the inputs, the targets, then we need to pass the number of epochs, let's say 50 for example, and the learning rate, let's say 0.1. And yeah, and we need some dummy data, so for the inputs and for the targets. Now, I want to, as I mentioned earlier, I want to train our network so that it will be able to compute the sum operation. So I'm gonna just like copy paste a ready-made like data set like for this, and so I'm not gonna like explain everything here because like this is like not the point, but so first of all, like we need this random function, and so we need to import a random here, otherwise it's not going to work. So we'd say from random import random, and so we have that now down here. Yeah, which is good. Okay, so now we should have, but let's call this inputs, and let's call this like targets. Right. Okay. So what's the point of this? Yeah, this fancy like list comprehensions like with arrays and things like that. Well, basically this is going to be an array where we have so something like this. So this is going to be like an array where we have this type of structure here. So say like 0.1, 0.2, and then we have another over here. And so these are like each of these guys in here is going to be a sample that we pass to forward propagation, right? And then we have the targets, and the targets are similar to this, but it's just like the sum over here. So instead of having like two values, you're just going to have one, which is 0.3 in this case, and this is going to be 0.7. Right, this is items is not correct, so we'll just need to move it from inputs. And right, so this is fine now. Good. So now if everything is correct, now we should be able to train our multi-layer perception from scratch. Let's see if it works. Whoa, this is working, and that's fantastic because we have also a very nice report over here. So we started with this error at epoch 0, and then all the way through we went down, down, down at each epoch until we reached this error over here. And so as you see, the training is working because the error is going down, and so the network is slowly learning to do something very simple, which is like the sum operation. Someone could say, well, this is really like overkill to do like some sum, but I mean, yeah, that's what it is, right? Okay, so now we've like implemented like all backpropagation, gradient descent. We have an amazing MLP. So now what remains to do, like the last thing that we said we would do, is make some predictions, right? Okay, so how do we do that? So yeah, this is again quite simple. So yeah, let's create dummy data. And this time, let's call this input, and we do np dot array. And here we want to pass in, let's say 0.3 and 0.1. Good. And now we want our target, and we know that our targets should be the sum of those two numbers, so 0.4. Right, and so now what we need to do is MLP, damn it, MLP dot forward propagate, and then we want to pass in the input, and then we expect some output, right? So the idea, like the whole like train like a thought here is we have like our training data set. We build like our MLP, we train our MLP, and now we create some dummy data and we pass that in forward propagate so that we'll get like a prediction out there. So let's see how this prediction is doing. And so in the meantime, we'll do like just a print to give us a couple of prints to give us like a couple of new lines. And then we'll do print, and we'll say, so let's say this. So let's say our network believes that this plus this is equal to this, right? Now we need to pass all of this information in. So our beliefs that input, so this is input 0, this is input 1, and finally this is our target, right? Well, no, it's not our target, sorry, it's our output. Cool. Output calculation in 0, right? Okay, so let's run this and see if our network is going to be able to compute this, right? And right, so let's do that, and let's see. Nice, super good. So we have it here. Nice. So our network believes that 0.3 plus 0.1 is equal to 0.3996. Nice. So this is really close to our target, which is 0.4, right? So this is like quite good actually. So we made it. We trained our network. We have this like network which is an absolute overkill for calculating like the sum operation, but yeah, we made it. But apart from like the toy application, I think like what we've made it here like is quite something, because we made to basically build a whole neural network, feed-forward neural network, multi-layer perception from scratch. And now we have all of the different elements to it. We have forward propagation, we have back propagation, we have gradient descent, we know how we can train it. Everything like is super modular, because you can put like as many layers in the network as you want, and you can specify as many like neurons as you want. Like, so that's like also like a really nice. And so yeah, I think like we should just like congratulate ourselves, because I guess like we know way more than most people out there who are also like machine learning practitioners, because like we know how to build a neural network, a simple neural network from scratch. Good. So this was it for this very, very long video. I hope you enjoyed it. And if you did, please subscribe and hit the notification bell so you'll just like get new videos when they are uploaded. And then for the next time, what we'll do is we're gonna basically build something very similar to this with TensorFlow, and you'll see that all the time that we spent like doing this, it's going to take, I don't know, like probably a tenth like of the time and the number of like lines of code for doing that. And so yeah, we'll get into TensorFlow and Keras, and we'll build a simple MLP from scratch. So stay tuned and like this video, and I'll see you next time. Cheers.